Today, we shall study about junction transistor in semiconductor electronics. The credit of inventing the transistor in the year 1947 goes to J. Bardeen and W. H. Brattain of Failed Telephone Laboratories, USA. That transistor was a point contact transistor. The first junction transistor consisting of two back-to-back PN junctions was invented by William Shockley in 1951. As long as only the junction transistor was known, it was known simply as transistor. But over the years, new types of transistors were invented, and to differentiate it from the new ones, it is now called the bipolar junction transistor, BJT. Even now, often the word transistor is used to mean BJT when there is no confusion. Since our study is limited to only BJT, we shall use the word transistor for BJT without any ambiguity. Transistor structure and action. A transistor has three doped regions forming two PN junctions between them. Obviously, there are two types of transistors as shown in figure A, capital A. NPN transistor first. Here the two segments of N-type semiconductor, emitter and collector, are separated by a segment of P-type semiconductor base. Second is PNP transistor. Here the two segments of P-type semiconductor termed as emitter and collector are separated by a segment of N-type semiconductor termed as base. The schematic representation of an NPN and PNP configuration are shown in figure A. All the three segments of a transistor have different thickness and their doping levels are also different. In the schematic samples used for representing PNP and NPN transistor, the arrowhead shows the direction of conventional current in the transistor. A brief description of the three segments of a transistor is given below. Emitter. This is the segment on one side of the transistor shown in figure A. It is a moderate of size and heavily doped. It supplies a large number of majority carriers for the current flow through the transistor base. This is the central segment. It is a very thin and slightly doped collector. This segment collects a major portion of the majority carrier supplied by the emitter. The collector side is moderately doped and larger in size as compared to the emitter. Now, in case of transistor depletion, regions are formed at the emitter base junction and base collector junction. For understanding the action of a transistor, we have to consider the nature of the depletion region. Formed at these junctions, the charge carriers move across different regions of the transistor. When proper voltages are applied across its terminals, the biasing of transistor is done differently for different uses. Basically, it was invented to function as an amplifier, a device which produces a enlarged copy of a signal, but later its use as a switch acquired equal importance. We shall study both these functions and the ways the transistor is biased to achieve these mutually exclusive functions. First, we shall see what gives the transistor its amplifying capability. The transistor works as an amplifier with its emitter base junction forward biased and base collector junction reverse biased. This situation is shown in figure 1, where VC and VE are used for creating the respective bias. When the transistor is biased in the way, this way it is said to be inactive state. We represent the voltage between emitter and base as VEB and that between the collector and the base as VCB. In figure 1, base is a common terminal for the two power supplies. When other terminals are connected to the emitter and collector respectively, so the two power supplies are represented as VEE and VCC respectively. In circuits where emitter is the common terminal, the power supply between the base and that emitter is represented as VBB and that between collector and emitter as VCC. Let us see now the path of the current carriers in the transistor. With emitter base junction forward biased and base collector junction reverse biased, the heavily doped emitter has a high concentration of majority carriers, which will be holes in a PNP transistor and electrons in an NPN transistor. These majority carriers enter the base region in a large numbers. The base is thin and lightly doped, so the majority carriers there would be few. In a PNP transistor, the majority carriers in the base are electrons in the bases of N-type semiconductor. The large number of holes entering the base from the emitter swamps the small number of electrons there. As the base collector junction is reverse biased. Thus, these holes which appears as minority carriers at the junction can easily cross the junction and enter the collector. The holes in the base could move either towards the base terminal to combine with the electrons entering from outside or cross the junction to enter into the collector and reach the collector terminal. The base is made thin so that most of the holes find themselves near the reverse biased base collector junction and so cross the junction instead of moving to the base terminal. It is interesting to note that due to the forward bias, a large current enters the emitter base junction, but most of it is diverted to adjacent reverse bias base collector junction, and the current coming out of the base becomes a very small fraction of the current that enters the junction. If we represent the whole current and the electron current crossing the forward bias junction by IH and IE respectively, then the total current in a forward biased diode is the sum IH plus IE. We see the emitter current IE barabar IH plus IE, but the IE barabar IH plus IC, but the base current IB is very smaller than IH plus IC, because the major part of IE goes to collector instead of coming out of the base terminal. The base current is thus a small fraction of the emitter current. The current entering into the emitter from the outside is equal to the emitter current IE. Similarly, the current emerging from the base terminal is IB and that from collector terminal is IC. Thus, the emitter current is the sum of collector current and base current, IE barabar IC plus IB. We also see that IC barabar IE, our description of the direction of motion of holes is identical with the direction of the conventional current, but the direction of motion of the electron is just opposite to that of the current. Thus, in a PNP transistor, the current enters from emitter to base. In a PNP transistor, from emitter to base, and in NPN transistor, it enters from base to emitter, base into emitter. The arrowhead in the emitter shows the direction of the conventional current. In active state of the transistor, the emitter base junction acts as a low resistance while the base collector acts as a high resistance.